Hi there, welcome to Lecture 9. So the purpose of today's lecture is we're going to learn how to use JASP to compare group means. Now you might be a little surprised to hear this because if you've been paying attention this semester, you know that you already know how to do this, at least for simple data sets. That is, if you have one group mean that's being tested against some hypothesized population mean, think about the examples that we've done with, this IQ treatment is supposed to improve IQ over the population mean of 100. Then we know what to do. We use a single sample t-test. If you have two means that come from paired samples, so for example, you have people who are taking a test before some treatment and then a test after the treatment, this so-called pre-test, post-test design, then you know that you use a paired samples t-test. And finally, you know that if I want to compare two means that come from independent groups, so for example, an experimental treatment and a control treatment, then you know that we use the independent samples t-test. You know how to do these, you know how to do them by hand. But when you have more complex data sets, it is very helpful to not have to do these by hand. And so we'll use JASP to do them, but you still need to know the mechanics of how they work, and particularly important, how do you interpret the results of those tests. And then finally, one of the things that we're going to introduce today is we're going to learn how to compare three or more group means. So all of the examples we've done so far, we have talked about how to compare two group means, exactly two. But what happens when you want to use three or more? Well, t-test will no longer work, but we're going to use something called Analysis of Variance, or ANOVA for short. And it's an easy couple of clicks in JASP to implement this new technique. So the first thing that we need to do before we can use JASP is we need to remember how hypothesis testing works. When we get to JASP, it's just going to be some quick pointing and clicking and everything's going to be done. We need to remember what's really going on under the hood. So remember, to do hypothesis testing, the first thing that we have to do is we have to define a null hypothesis and an alternative hypothesis. So a null hypothesis, of course, is a hypothesis of no difference between the groups or no effect, depending on how you're characterizing this. And an alternative hypothesis is there is some difference. It could be that you're predicting that one group is greater than the other. That's called a directional hypothesis. Or it could be that you're predicting that they're just different from each other. We're not really predicting a priori which one's bigger or not. That's called a non-directional hypothesis. Regardless, these hypotheses are called models of the potential data that we could observe. So we set up these models or these hypotheses, and then we actually observe our data. And then we basically want to figure out how good are these models at predicting our data. So here's what we do. We assume that the null is true. That's important. In fact, you'll recall on homeworks and exams, I absolutely want you to write down, assume the null is true. The reason is because everything from here is based on that assumption. So we assume the null is true, and then we calculate the probability that you could have observed that data, or more extreme. So how do we do that? Well, it requires computing a test statistic. Now, we haven't called it that because all we've dealt with so far are these t-scores. When we do a t-test, we compute a t-score. You'll recall before we even did t-tests, we did z-scores. Regardless of the specific label and the specific type of statistic that we compute, it is called in general a test statistic. Then we compute the probability of observing this test statistic under the null, under the assumption that the null is true, and that probability is called a p-value. Now, if that p-value is small, so we usually set 0.05 as our threshold for small, but of course there is some argument about what really is small when it comes to p-values. If that p-value is small, then that means that our data is rare. That is, it is quite unlikely to have happened if the null were true. And so if our data is rare, well, we have the data here, so it must be the case that it was the hypothesis that was wrong. So we reject the null, and that leaves us with indirect support for the alternative. So this should not be new to you. This is exactly how hypothesis testing works, and this is what we've been doing all along. But we need to keep this in mind when we open up JASP. So what I want to do in this lecture is I want to illustrate doing some of these hypothesis tests in JASP with a data set. So on Canvas, you can download a file called Sternberg.csv, and you can open it in JASP. Now I'm going to briefly show you in Canvas where that is and how you find it. So here's Canvas. Now, of course, depending on when you're watching this video, your Canvas may look a little different from this, but somewhere around where you linked to this lecture is a file called Sternberg.csv. Now, if you're on a Windows machine, you'll want to right-click on this. If you're on a Mac, there is no right-click, so you press Option-click. So I'm holding, or sorry, not Option, that was incorrect. You click Control-click. So I'm going to hold down the Control button and then click. It's going to open up a dialog box, and basically I want to save this file somewhere. So I'm going to say Save Link As, and I'm just going to put it on my desktop. Now it's already there from earlier, so I'm not going to save it, but that's how you get it. Save the file somewhere on your desktop. Then we're going to open up JASP. So let me go to JASP, and I'm going to click here to open, and I'm going to navigate on my computer to where I saved that file. So for me, that was the desktop. And I'm going to find that file. Now, JASP should gray out everything except for CSV files, because you'll remember in JASP, that's what you want for file structures to be. So we'll open up this CSV file. And we now have a nice big data set. In fact, it's big. It's got 300 observations in it. We certainly wouldn't want to do that by hand. What are all of these variables? Well, let's go back to the lecture notes and let's find out what those variables are. Well, what is this? Sternberg in 1966 examined how people recall things from short-term memory. Right around the late 60s, he was very interested in this question, particularly the cognitive architectures of short-term memory. So this data set is from an experiment where he did the following. On a screen, he briefly presented a set of either 1, 3, or 5 digits. So that was a manipulation in his experiment. Shortly after this presentation of those digits, he then presented a single test digit on the screen and asked subjects to press one of two buttons. To press yes if the test digit had been included in the original set, and no if the test digit was not included in the original set. So basically what he was doing was testing short-term memory, and particularly measuring how long it took people to press the yes or no button. So that information is encoded in this Sternberg.csv data file as follows. There's a variable called nstem. It's simply the number of stimuli, which are digits in this case, and it's either 1, 3, or 5. There's a column or variable for yes, no, and that is simply a binary variable which is coded 1 for yes responses and 2 for no responses. And in fact, now that I think about that, that is absolutely incorrect. Let's go back to JASP. No, that is absolutely correct. Never mind. I got ahead of myself. So 1 for yes responses and 2 for no responses. And then finally, a variable called RT, which is simply the response time, and it's measured in milliseconds. So let's just look at this data file. You can see we've got the nstem. These values are 1, 3, and 5. In fact, a quick way to see that is simply click on the label itself, and it'll open up a little filter dialog. It shows you what the different values are. We can do the same thing with yes, no. There's 1s and 2s. And then, of course, this one, this RT column, this has numbers, and these represent milliseconds. So 400, 410, 470 milliseconds. So these are your response times. So let's just hit X to get rid of that. Okay, so we're ready to do some hypothesis testing. We're actually going to do both examples with this data set, so that makes the lecture nice and tidy. But let's see what these examples are. Well, these examples are going to come from 2 specific research questions that I might be interested in. So here's research question number 1. Is there a significant difference in the mean RTs, so again, response times, for trials where the test digit was in the original comparison set, so yes responses, compared to trials where the test digit was not in the original comparison set, so the no responses? So basically, we're comparing, are the yes responses different in terms of speed than the no responses? So you have two means from these two independent samples. So the first step is to identify the test we're going to use. We're going to use the independent samples t-test. Again, because we have two means and we have two independent samples. Now the second part, this is where we define our parameters and write down our hypotheses. So we might set mu1 to be the population mean response time for yes responses, and mu2 to be population mean response time for no responses. Now, of course, you can write these in the opposite order if you want, but I think it makes good sense to write them this way. Once we've written down what those two parameters are, then we can write down two hypotheses. First one is the null hypothesis, H0, and that, of course, is the hypothesis that there's no difference. So we would say mu1 equals mu2. And then H1, the alternative, we would call that one, we're not predicting any specific difference, right? We're just asking if there is a difference. So we would simply say mu1 is not equal to mu2. Then, once we've done that, we are ready to perform the test in JASP and interpret the resulting p-value. And based on that p-value, make a conclusion about our research question. Okay? So let's go to JASP and do just that. So how does this work? Well, your experience with JASP so far should lead you to remember that JASP is pretty intuitive. So if you want to do a t-test, all you've got to do is find where the t-tests are. And it's nice and easy to find this up here, this little t-test button. If I press on the button t-tests, it leads me to 6 options, but I only want one of these. I know it's an independent samples t-test, so I'm going to click that. And it opens up a dialog for independent samples t-test. Now, how does this work? Well, the way it works is you put the dependent variable into this box called variables. So this is the thing that you're measuring. These are what your mu's represent. The mu's represent response times, right? So I'm going to put RT into that box. These are the things that I'm wondering, is there a difference between two groups? Then the grouping variable itself, the variable that defines whether you're in the first group or the second group, that goes here, and that is yes, no in this case. Okay. So once I do that, there's really not much else to do because JASP automatically produces the independent samples t-test for me and gives me the t-score, the degrees of freedom, and the resulting p-value. So as you can see very quickly, I've got a t-score of negative 3.65 on 298 degrees of freedom. It's because our sample size were huge here. And the p-value is less than 0.001. Now, of course, when we have p-values this small, what does this mean? This means that our data are rare under the null. So if we assume there's no difference between them, our data would be very unlikely to occur. So what this tells us, of course, we've had practice with this before, this tells us we reject the null and we conclude that yes, there is a significant difference between the two groups. Now, there is a significant difference. That doesn't tell us which one is bigger, which one is smaller. To do that, we would have to specify an alternative hypothesis. And we didn't do that here, but as you can see, there are options for doing this. So if you are doing examples where you are testing a directional hypothesis, then you can specify using one of these two buttons which one of those that you use. And there are a lot of other options here. For example, one of them is the effect size. And I automatically then get a measure of Cohen's d. There are other effect sizes, of course, but I'm not too interested in getting that right now. I can also click descriptives. This will give me the descriptives for the groups. Okay. And in fact, if I click location parameter and confidence interval, it will give me a confidence interval, lower and upper, on the mean difference. So these things that you did in the previous lecture. So it gives me lots of output. But for my research question again was, are the mean response times different for yes and no? And the answer is yes. We rejected the null, which leaves support for H1, which is that they are different. So that's how you do an independent samples t-test. I'm going to go back to my lecture notes here, and let's now do one more example. And this is where we're going to introduce the analysis of variance. So the second research question is this: is there a significant difference in mean response times among trials with 1, 3, or 5 numbers in the original comparison set? So now you'll notice that we have 3 groups to compare. We want to compare the means for 1 number, 3 numbers, and 5 numbers. A t-test will not work for this. A t-test has to have exactly 2 groups. But there is another technique that will work just fine, and it's called the analysis of variance. Now, I'm not going to get too far into the mechanics of analysis of variance. There are other courses that you can take potentially in graduate school where you can really get into the nitty-gritty on ANOVA. But basically, it works like this. What we do is we compare the variance between groups to the variance within groups. And this then is used to compute something called an F statistic. Based on that F statistic and the assumption of a null hypothesis, you compute a p-value. So past that, the mechanics are exactly the same. We've got to define a null, an alternative, compute a statistic, and then compute a p-value. The details, of course, you can read in Chapter 2 of our textbook, Learning Statistics with JASP. But for now, let's just jump into the hands-on how do you do this. Well, first step, of course, from last time, identify the test to use. Since we have 3 or more means, we have to use the ANOVA. Then we define the parameters and write down our hypotheses. Well, because we have 3 means we're comparing, we have then 3 population means, which I'll denote mu1, mu2, and mu3. Mu1 is the population mean response time for displays with 1 number. Mu2, same thing, but with 3 numbers. Mu3 is the third one. It's the same thing, but for displays with 5 numbers. Now, how do you write the null and alternative? Well, the null is that all the means are equal. Mu1 equals mu2 equals mu3. The alternative is essentially not this, all right? So not that mu1 equals mu2 equals mu3. So a concise way to write that, I think, is not all the mu's are equal. And what this means is that there are differences among these population means. Now, unfortunately, it doesn't tell you which one is different from the others, and you have to do some other things to answer that, but that's beyond the scope of this lecture. So given this this null hypothesis and this alternative, we are ready to perform the test in JASP, and as before, we're ready to interpret the p-value and make a conclusion about our research question. So let's go back to JASP. Now this time, we got the same data. You can see that over here. Use these little arrows to click back and forth between the data and the analysis screen. But this time, we're going to go to the ANOVA button. Now there are 7 options, but the one we want is ANOVA. Okay. The dialog box looks very similar to the one for t-test. This time, of course, the dependent variable is still RT. But this time, what we call fixed factors is is our grouping variable, and that's number of stimuli. So we'll stick that in there. And immediately we see the output down here. Now the output looks a lot different because it makes what's called an ANOVA table. But what you're looking for are 2 numbers. You're looking for this F statistic. So this F statistic is 33. And what that then translates to directly that we can interpret is a p-value. And you'll notice again, for this research question, our p-value is very small. What does that mean? Well, remember, we assume the null, which means that we assume that the population means are equal. Then our data is very rare. It's less than 5% likely to occur under this null hypothesis. What we then do is we say, well, it's very unlikely for us to have gotten this data under the null. The null must be false. So let's reject the null. So we're rejecting the null, and what that tells us, go back to our lecture screen, what that tells us is that leaves us support for H1, which means that not all the mu's are equal. So for this research question, that tells us that yes, there is a significant difference in these mean RTs between 1, 3, and 5 numbers. So the mechanics of the hypothesis test works exactly the same. How it's computed is different, but I don't think that's important. If you can do it in JASP, you can interpret it just the same as you do with the t-test. So that's what I wanted to cover for this lecture. Wanted to introduce how to do hypothesis testing, particularly comparing means, but other hypothesis tests work just fine. I'll mention in JASP there are all kinds of hypothesis tests that you can do, not only t-tests and ANOVA, but you can also do correlations, regressions, you can do tests of frequencies, counts, you can do lots of cool things. but we'll do those things in other courses. So that's all for now. Hope you, if you have any questions, please let me know. And that's all for now. I'll see you next time.